a foundation for decision-making. Analytics is a scientific approach to decision-making. It seeks optimal solutions to complex problems, often involving scarce resources, using mathematical models and analytical methods originating in World War II. Military planners used it for strategic problems, optimizing radar deployment and improving bombing efficiency, now applied in various sectors. Analytics involves defining problems, modeling, and analysis. It's multidisciplinary, drawing from many fields, helping solve logistics, finance, and healthcare issues. Analytics supports decision-making with powerful tools, leading to better resource allocation and efficiency. Analytics shapes the efficiency of systems we use daily. The symbiotic relationship, analytics and computational power. Analytics relies on computational tools. Real-world systems are complex, numerous variables and vast data. Computers handle this complexity. They build and solve models, enabling optimal decisions. Visualization aids understanding, bridging math and business intelligence. The age of ingenuity. Manual methods in early analytics. Before computers, analytics relied on manual methods requiring ingenuity and effort. Early analytics problems were tackled using basic mathematical tools. These included graphical methods, slide rules, and mechanical calculators. Large-scale optimization was out of reach. Despite challenges, foundational analytics concepts were developed. Pioneers like George Dantzig created algorithms like the CPLEX method. Manual methods proved analytics' value and led to early software development. Pioneering the digital frontier, the genesis of analytics software. The advent of electronic computers in the late 1940s marked a turning point for analytics. These machines, though limited, offered a glimpse of a future where complex calculations could be automated. Analytics pioneers began exploring how these devices could be harnessed. Early efforts focused on implementing cumbersome algorithms. Linear programming was an early candidate for computerization. The development of the first OR software required expertise in both mathematics and computer programming. Despite limitations, these early programs represented a monumental leap forward. They could solve problems in hours that would have taken weeks manually. These early successes set the stage for rapid advancements in OR software. The algorithmic revolution transforming analytics with automated solvers. The transition from manual calculations to algorithmic solvers revolutionized analytics. Algorithmic solvers automate complex calculations, freeing practitioners to focus on problem solving. This shift enabled faster, more accurate, and larger-scale problem-solving. It transformed analytics from an academic discipline into a practical business tool. Algorithmic solvers are now indispensable across diverse industries. The computational dawn analytics enters the 1950s. The 1950s marked a transformative period for analytics. Foundational mathematical theories were established. Practical application was hindered by the volume of calculations. The dawn of the electronic computing age was breaking. Machines like the UNIVAC 1 and early IBM mainframes appeared. These computers offered unprecedented computational speed. They filled large rooms and required specialized staff. Their memory was scarce and their processing capabilities were modest. Analytics practitioners quickly recognized the potential. Analytics techniques like linear programming were ideal for automation. Early interactions between analytics experts and computer programmers began. The main challenge was translating abstract mathematical procedures. Programming languages were still in their infancy. Instructions had to be written in machine code or basic assembly languages. This made the development process slow and prone to errors. Despite these hurdles, the allure of automated computation was strong. The ability to solve larger problems and achieve accurate results was significant. Early efforts focused on implementing well-understood algorithms. The goal was to tackle problems previously considered computationally infeasible. These pioneering endeavors were critical. They demonstrated proof of concept and built momentum for further investment. The vision was clear. Computers could become powerful engines for rational decision-making. The successful application of analytics during World War II had proven its value. The challenge was to transition these techniques into the post-war industrial sectors. Businesses faced increasingly complex logistical, production and resource allocation problems. Manual methods of analytics could not scale effectively. Early computers were not just a convenience, they were essential tools for unlocking the full potential of analytics. IBM's pioneering leap commercializing linear programming solvers. IBM played a pivotal role in commercializing analytics software. They developed early linear programming solvers for their mainframes. These solvers showcased IBM's hardware capabilities and provided value to customers. This move legitimized analytics as a practical business tool. It spurred demand for more powerful computers and sophisticated software. IBM's commitment created a market and skilled practitioners in analytics. The simplex method in Silicon early digital implementations. The simplex method developed by George Dantzig in 1947 was key for solving linear programming problems. Its iterative nature suited digital computers. Transitioning to machine execution was a milestone. Early programmers faced significant technical challenges. Limited memory required ingenious programming techniques. Data management often involved swapping data between memory and storage. Numerical stability was a major concern. Rounding errors could accumulate, leading to incorrect solutions. Programmers had to mitigate these numerical issues. Robust implementations required understanding both the algorithm and hardware. Each step of the algorithm had to be meticulously coded. Early digital solvers directly translated the manual simplex procedure. The program read problem data and initialized the simplex tableau. A loop performed simplex iterations, identifying pivot columns and rows. The process continued until an optimal solution was found. The final solution and objective function value were then printed. Successful implementations on computers like the IBM 704 demonstrated the power of this approach. The petroleum industry was an early adopter, optimizing gasoline blending and refinery operations. These early successes provided tangible evidence of the benefits of computerized analytics. They solved real-world problems more efficiently. This spurred further research into improving the simplex method and developing more advanced LP software. The simplex method solidified its central role in analytics. Fortran's arrival, a new language for scientific computation. The mid-1950s saw the creation of Fortran by IBM's John Backus. Released in 1957, Fortran simplified scientific programming. It replaced tedious assembly language with high-level code. Fortran's impact on analytics was profound. It democratized software development and fostered innovation. Fortran became the standard for scientific programming. Building with Fortran custom analytics models emerge. The 1960s and 1970s saw a surge in custom analytics models with Fortran addressing specific industry needs with precision. Fortran enabled the implementation of various analytics methodologies, including network models and algorithms like Dijkstra's. Early simulation languages and inventory control models were also built upon Fortran. Despite challenges, Fortran expanded the scope of analytics across many sectors. In the 1970s and early 1980s, analytics software evolved significantly, driven by advancements in hardware and algorithms. Fortran-based LP solvers improved, enabling more complex problem-solving. Universities and large organizations led these advancements. Enhanced computational power allowed for larger, more complex analytics problems. Linear programming solvers saw significant advancements. Algorithm developers refined techniques like the revised simplex method. These improvements led to faster, more stable solutions. Companies could model larger operations with greater fidelity. Mixed integer programming gained attention despite challenges. Better presolved techniques and cutting plane methods emerged. Simulation software matured, offering more features. Statistical analysis packages also grew in capability. Universities and research institutions drove innovation. Integrated software systems began to emerge. This era laid the groundwork for the personal computer revolution. The experience with Fortran-based systems provided valuable lessons. The analytics community learned about practical implementation challenges. This knowledge shaped the next generation of analytics tools. These tools transformed industries worldwide. The early 1990s marked a significant turning point for analytics software. Existing tools, often developed in Fortran, began to show their limitations. Many of these programs were designed for mainframe computers. Personal computers and workstations, however, were rapidly increasing in power. This shift in hardware capability created new possibilities. Businesses faced increasingly complex problems. They required more sophisticated and accessible analytics tools. The stage was set for a new generation of software solutions to emerge and transform the field for all users. There was a growing demand for software that was easier to use. Analytics practitioners needed more than just raw solver speed. They sought integrated environments for modeling, solving, and analyzing results. Command line interfaces, common at the time, were often cumbersome. They hindered broader adoption of analytics techniques within organizations. The ideal software would allow users to express models intuitively. It would also provide clear interpretations of the solutions. This user-centric approach was becoming increasingly important for practical success. Early signs of this much-needed change began to appear slowly. New commercial software companies started to explore the analytics market. They aimed to provide more polished and robust tools. The academic community continued its vital role in innovation. Researchers developed new algorithms and prototype software. However, a gap often existed between these academic creations and commercially viable products. The anticipation for software that could handle larger, more intricate models efficiently was palpable among practitioners looking for real solutions. Analytics professionals faced specific challenges during this period. Handling large datasets for complex models remained a cumbersome task. The visualization of solutions and model structures was often primitive or non-existent. This made it difficult to communicate findings effectively to decision-makers. There was a strong desire for faster turnaround times. Professionals wanted to move quickly from model formulation to actionable insights. This environment created a fertile ground for the disruptive software technologies that were about to define the decade for analytics. MATLAB emerged as a powerful force in numerical computation during the 1990s. Its name stands for Matrix Laboratory. It was originally created in the late 1970s by Cleve Moeller. Moeller was then chairman of the computer science department at the University of New Mexico. His initial goal was to give his students access to LINPACK and ISPACK libraries without them needing to learn Fortran. The software quickly gained traction beyond his initial classroom intentions due to its unique strengths and focus. It was designed from the ground up for matrix manipulation and numerical analysis, a key need. The core philosophy behind MATLAB was its interactive environment. It treated the matrix as its fundamental data type. This design choice greatly simplified many numerical tasks. Engineers and scientists found it remarkably easy to use. They could express complex mathematical operations with an intuitive syntax. This was a stark contrast to traditional programming languages like Fortran or C. MATLAB's command-driven interface allowed for rapid experimentation and iteration. This interactive nature accelerated learning and development for many users across different fields of study. Early adoption of MATLAB was particularly strong in academia and engineering disciplines. It became a standard tool for teaching courses in linear algebra, numerical methods, and signal processing. Researchers used MATLAB extensively for algorithm prototyping and data analysis. Its intuitive syntax for mathematical operations allowed them to focus on the problem, rather than programming complexities. This ease of translation from mathematical concepts to executable code was a significant advantage. It fostered innovation and sped up the research cycle in many important scientific domains that needed it. MATLAB differed significantly from established languages like Fortran or C. It required much less boilerplate code to perform common numerical tasks. A vast library of built-in functions covered areas from basic arithmetic to advanced transformations. Crucially, MATLAB also incorporated powerful visualization capabilities from an early stage. Users could easily plot data and results in 2 or 3 dimensions. This graphical output was invaluable for understanding complex data and model behavior. These features collectively made MATLAB a highly productive environment for technical computing. MATLAB's foray into analytics, optimization and simulation capabilities. MATLAB's inherent strengths made it a natural fit for many analytics problems. Numerous analytics models rely heavily on matrices and linear algebra. Concepts like constraint matrices in linear programming are directly representable. MATLAB's matrix-oriented syntax allowed analytics practitioners to formulate and manipulate these models with relative ease. This was particularly true for those already comfortable with mathematical notation. The transition from textbook equations to MATLAB code was often straightforward. This accessibility was a major draw for people in the analytics community. Recognizing the needs of the analytics community, the MathWorks developed specific toolboxes. The optimization toolbox was a key addition for analytics practitioners. It provided functions for solving a variety of optimization problems. These included linear programming and non-linear programming. Quadratic programming and least squares problems were also covered. While not initially as powerful as dedicated solvers for very large problems, these tools were invaluable. They allowed for rapid prototyping and solving of moderately sized optimization models directly within the MATLAB environment, which was helpful. MATLAB also proved useful for simulation tasks in analytics. Its flexible scripting language allowed users to build custom discrete event or continuous simulation models. Researchers could model systems like queues, inventory systems, or manufacturing processes. The results of these simulations could then be analyzed using MATLAB's extensive statistical and plotting functions. The ability to visualize simulation outputs graphically greatly aided in understanding system dynamics. This made MATLAB a versatile tool for both optimization and simulation aspects of analytics studies for many people. The impact of MATLAB on analytics education and research was profound. It enabled faster prototyping of new algorithms and solution techniques. Students could learn analytics concepts more effectively through interactive examples and visualizations. Instructors could easily demonstrate the behavior of different models and algorithms. Complex ideas became more tangible when implemented and explored in MATLAB. This contributed to a more hands-on and experimental approach to learning and research in the analytics field. The software empowered a new generation of analytics professionals in many ways. As the 1990s began, there was a clear and growing need for dedicated, high-performance optimization solvers. Linear programming and mixed integer programming problems arising in industry were becoming increasingly large. The scale and complexity of these models often overwhelmed existing software tools. Many businesses required solutions to these massive optimization problems in a timely manner. Existing academic codes or general-purpose mathematical software often struggled with the speed and robustness needed for these demanding industrial applications. This created an opportunity for specialized solutions. It was in this context that Dr. Robert E. Bixby co-founded CPLEX Optimization, Inc. in 1987. Bixby, a renowned professor in the field of mathematical programming, had a clear vision. He aimed to create a commercial LP solver that would significantly outperform existing options. The primary focus was on raw computational efficiency and algorithmic sophistication. The goal was to develop software that could reliably solve the largest and most challenging LP problems faced by industry. This ambition required deep expertise in both analytics algorithms and software engineering to succeed. The initial release of CPLEX quickly made a substantial impact. It set new performance benchmarks for solving linear programming problems. This superior speed was achieved through advanced implementations of the simplex method. It also included state-of-the-art numerical techniques and careful software engineering. CPLEX was designed from the outset to be robust and reliable. It could handle numerically challenging models that caused other solvers to fail. This combination of speed and stability was exactly what industrial users were seeking for their critical applications. CPLEX offered several key features that contributed to its rapid adoption. Its simplex solvers, both primal and dual, were exceptionally fast and robust. It soon incorporated barrier methods, offering an alternative solution path for certain types of LP problems. Crucially, CPLEX also began to develop strong capabilities for mixed integer programming. MIP problems are significantly harder to solve than LPs. CPLEX's focus on tackling these difficult industrial strength problems distinguished it. It quickly became the solver of choice for organizations facing complex optimization tasks across many different areas. Section 5. CPLEX's dominance tackling industrial-scale optimization challenges. The superior performance of CPLEX led to its rapid adoption across various industries. Companies in supply chain management and logistics were among the early adopters. They used CPLEX to optimize routing, scheduling, and facility location decisions. The manufacturing sector applied it for production planning and resource allocation. Financial institutions utilize CPLEX for portfolio optimization and risk management. The ability to solve previously intractable large-scale optimization problems provided significant competitive advantages. These companies could now make more informed and efficient decisions based on data. CPLEX maintained its market leadership through continuous improvement and innovation. The software underwent regular updates, each bringing faster algorithms and enhanced capabilities. Particular attention was paid to improving its mixed integer programming technology. This involved developing more effective cutting plane strategies. Advanced heuristic techniques were also incorporated to find good solutions quickly. The CPLEX development team constantly pushed the boundaries of what was possible in solving complex MIPs. This relentless pursuit of performance kept it ahead of competitors for a long time. A key factor in CPLEX's success was its design as a callable library. This allowed it to be easily integrated into other programming languages. Companies could embed CPLEX's optimization engine within their custom applications. It could also be linked with various modeling systems and languages. This flexibility made CPLEX an accessible and powerful component in larger decision support systems. It effectively became an industry standard for high-performance optimization. Many other software tools began to offer interfaces to CPLEX as their underlying solver for tough jobs. The impact of CPLEX on the quality of decision-making was substantial. It enabled organizations to build more sophisticated and accurate OR models. These models could better reflect the true complexities of their operations. The resulting solutions often led to significant cost savings and efficiency gains. For many companies, the return on investment in CPLEX was very high. It transformed optimization from a specialized academic pursuit into a practical and valuable business tool. This helped to elevate the profile and impact of analytics within the corporate world significantly. A transformative decade, MATLAB and CPLEX redefining analytics practices, 1990s to 2000s. MATLAB and CPLEX, while both influential, played distinct roles in the analytics software landscape of the 1990s and early 2000s. MATLAB offered a versatile environment for general numerical computation. It excelled in algorithm prototyping, data analysis, and visualization. Its optimization toolboxes provided good capabilities for a range of problems. CPLEX, on the other hand, was a specialized high-performance engine. Its singular focus was solving large-scale linear and mixed integer programming problems with maximum speed and robustness. These different strengths catered to different needs within the analytics community. Despite their differences, synergies often existed between MATLAB and CPLEX. Many analytics practitioners used MATLAB for model development and data pre-processing. They would then call CPLEX as the back-end solver for the core optimization task. The results from CPLEX could then be imported back into MATLAB for post-processing and visualization. Academic researchers often favored MATLAB for its flexibility in exploring new ideas. Industrial users facing massive problems frequently relied on CPLEX's raw power. Both tools contributed to enhancing productivity and capability for their respective users. The overall impact of these software packages on the analytics field was transformative. They significantly increased the productivity of analytics professionals. Model development and solution times were drastically reduced for many types of problems. This allowed for more extensive analysis and scenario testing. The improved accessibility and power of these tools also led to a wider acceptance of analytics methods in business and industry. More organizations began to see the value of data-driven optimization. This helped to expand the reach and influence of the analytics discipline. The advancements driven by MATLAB and CPLEX during this period set the stage for the next wave of innovation in the 2000s. Users now had higher expectations for analytics software usability and performance. The success of these tools also highlighted the benefits of specialized solvers and integrated modeling environments. This paved the way for the development of algebraic modeling languages. These languages would further simplify the process of translating complex business problems into solvable mathematical models. The legacy of the 1990s was a more mature and capable analytics software ecosystem. The open source wave democratizing analytics tools. The 2010 S witnessed a significant shift in the software landscape. The open source movement gained incredible momentum. It offered an alternative to proprietary commercial software. This philosophy emphasized collaboration, transparency, and community-driven development. For analytics, this meant new possibilities for accessing and developing powerful analytical tools. Open source tools eliminated licensing fees, making sophisticated capabilities accessible to a broader audience. This openness fostered innovation and wider adoption of analytics techniques. The entire field of analytics benefited from this increased competition and the democratization of powerful analytical capabilities. Pyomo, flexible optimization modeling in the Python ecosystem. Pyomo is a Python-based open-source software package. It supports diverse optimization capabilities developed at Sandia National Laboratories and UC Davis. Pyomo integrates deeply with Python. It offers flexibility in model expression. Pyomo supports a wide range of problem types. It provides interfaces to various solvers. Pyomo is widely used in academia and industry. It empowers analytics professionals to develop advanced optimization solutions. Artificial intelligence meets analytics, a new synergy. The 2010 S saw the rise of artificial intelligence, particularly machine learning. This created exciting new synergies with analytics. Analytics focuses on optimal decision-making, while AI offers techniques for learning from data and making predictions. Combining these fields creates robust, adaptive decision support systems. Analytics structures and solves complex decision problems. AI enhances these models by providing better inputs and navigating solutions efficiently. Scaling new heights, analytics software in the cloud computing era. Cloud computing platforms like AWS, Azure, and Google Cloud have revolutionized analytics software deployment. They offer vast, on-demand computational resources. This has democratized high-performance computing for analytics practitioners. Historically, solving large optimization problems required significant investment in server hardware. Cloud computing eliminates this barrier. It allows access to unlimited processing power on a pay-as-you-go basis. This scalability and flexibility are transforming analytics solutions across industries. Section 5. Case Study. CPLEX's enduring impact on modern supply chain optimization. CPLEX, introduced in the 1980s, remains a leading optimization solver. Its impact is evident in supply chain and logistics modeling. Modern supply chains are complex systems. They span global networks of suppliers, manufacturers, distributors, and retailers. They face constant pressures from demand volatility, cost considerations, and potential disruptions. Effectively managing these intricate networks requires sophisticated analytical tools. CPLEX provides the optimization engine needed to tackle these challenges. Companies worldwide rely on CPLEX for supply chain optimization. Strategic network design involves determining optimal facilities. CPLEX solves complex models to minimize costs while meeting service requirements. For tactical planning, CPLEX optimizes inventory levels. It balances holding costs against stock-out risks. Production scheduling models maximize throughput or minimize delays. In operational logistics, CPLEX optimizes vehicle routing and dispatch. It finds efficient routes for fleets to deliver goods. Models consider time windows, vehicle capacities, and regulations. CPLEX's algorithms enable optimal routing solutions quickly. This reduces transportation costs, fuel consumption, and delivery times. The benefits of using CPLEX in supply chain optimization are substantial. Companies report multi-million-dollar savings annually. Optimizing distribution networks lowers transportation and inventory costs. Better production scheduling increases asset utilization and reduces lead times. Enhanced vehicle routing reduces mileage and improves on-time delivery rates. CPLEX's ability to solve large models gives companies a competitive edge. It allows them to adapt to changing market conditions and design resilient supply chains. The integrated future analytics software in a connected, intelligent world. The evolution of analytics software is moving towards increasingly integrated and intelligent systems. Modern tools like Pyomo offer flexible modeling capabilities. Artificial intelligence techniques provide advanced data analysis and learning. Cloud computing delivers scalable computational power. These elements are not developing in isolation. Instead, they are increasingly being combined to create comprehensive decision support platforms. The future of analytics software lies in this powerful synergy. It aims to provide end-to-end solutions that seamlessly connect data acquisition, model formulation, solution generation, and insight delivery for users. We are seeing a trend where OR models are embedded within larger enterprise systems. These systems draw data from various sources in real time. For example, an advanced planning system for a manufacturer might use machine learning to forecast demand. This forecast then feeds into a Pyomo model that optimizes the production schedule. The optimization is run on cloud infrastructure for speed and scalability. The results are then visualized on a dashboard for planners. This level of integration allows for more agile and responsive decision-making. It helps organizations adapt quickly to changing conditions and opportunities in their respective markets. This evolving landscape is also changing the role of the analytics professional. While strong analytical and modeling skills remain essential, there is a growing need for expertise in data science, software integration, and cloud technologies. Analytics practitioners are becoming key players in multidisciplinary teams. They work alongside data engineers, AI specialists, and business analysts. The ability to communicate complex analytical insights effectively to non-technical stakeholders is more important than ever. The focus is shifting from simply solving isolated problems to designing and implementing holistic, data-driven decision intelligence systems. Looking ahead, the journey of analytics software is far from over. We can expect continued advancements in algorithms, solver technologies, and modeling paradigms. The integration with AI will deepen further, leading to systems that can learn and self-optimize with minimal human intervention. Emerging technologies like quantum computing, though still in early stages, hold the potential to revolutionize the solution of certain classes of analytics problems in the long term. Analytics, powered by increasingly sophisticated software, will continue to be a vital discipline. It will help organizations navigate complexity and make optimal choices in an increasingly interconnected and data-rich global environment. Comparing the Titans, an overview of Pyomo, CPLEX, and MATLAB in analytics. Choosing the right software is crucial in analytics. Pyomo, CPLEX, and MATLAB each offer unique strengths. Pyomo excels in flexibility, CPLEX in high-performance optimization, and MATLAB in numerical computation and integration. Understanding their core strengths helps in leveraging their capabilities effectively. The solver's dilemma: Pyomo's open flexibility versus CPLEX's commercial power. The choice between Pyomo and CPLEX presents a significant dilemma for analytics practitioners. Pyomo offers cost-effectiveness and transparency, ideal for academic institutions and startups. CPLEX provides dedicated support, comprehensive documentation, and robust performance for large enterprises. Pyomo excels in customization and integration within the Python ecosystem. CPLEX is unmatched in solving massive industrial-scale optimization problems. Industries like airlines, logistics, and finance rely on CPLEX for core operations optimization. MATLAB's engineering edge simulation and specialized analytics applications. MATLAB excels in numerical computation, matrix algebra, and engineering toolboxes. It's ideal for embedding analytics techniques within engineering analyses and simulations. Engineers use MATLAB for control systems, signal processing, and robotics. It integrates simulation and optimization, making it powerful for specific needs. Applied analytics. Selecting the right tool for common optimization scenarios. Selecting the right tool is crucial for solving analytics problems. For large-scale MIPs, use CPLEX with Pyomo. For custom algorithms, Pyomo in Python is ideal. MATLAB excels in simulating manufacturing processes. Often combining tools like Python, Pyomo, and CPLEX provides the best results. Strategic software selection: guiding principles for analytics practitioners. Choosing the right analytics software is crucial. Consider the problem type, model size, budget, and team expertise. Open source tools like Pyomo are cost-effective, while commercial options like CPLEX offer advanced features and support. Ensure compatibility with existing systems and consider future scalability. A strategic choice saves time and resources, ensuring long-term value. The unfolding horizon: future trends in analytics software. The journey of analytics software has been remarkable. It began with painstaking manual calculations. Now we have incredibly sophisticated computational tools. This evolution, however, is far from complete. The field continues to advance at a rapid pace. Researchers and developers relentlessly pursue more powerful, intuitive, and accessible decision-making aids. The future promises even greater integration of intelligence and automation within OR software. This will be driven by emerging technologies and the need to solve increasingly complex global challenges effectively and efficiently. The quest for better decision support remains a central theme. Artificial intelligence, particularly machine learning, is set to profoundly reshape analytics software. ML algorithms enhance analytics models by providing more accurate input data. For example, improved demand forecasts lead to better inventory and production plans. AI can also assist in the model formulation process itself. It can even automate the selection of the most suitable solution algorithms for specific problem types. Furthermore, reinforcement learning techniques are enabling the development of analytics systems that can learn from experience. These systems can make optimal decisions in dynamic and uncertain environments, adapting their strategies over time for improved performance. The role of cloud computing in analytics will continue to deepen and expand. Cloud platforms provide unprecedented scalability, allowing organizations to tackle massive optimization problems without large upfront hardware investments. This accessibility democratizes high-performance computing for analytics. It enables real-time decision optimization, crucial for dynamic systems like logistics or energy grids. We're also seeing the rise of analytics as a service models. These models offer specialized optimization capabilities on demand. The integration with big data analytics and serverless computing architectures further amplifies the power and reach of cloud-based analytics software solutions. Looking further ahead, quantum computing presents a revolutionary, albeit nascent, frontier for analytics. While still in its early developmental stages, quantum computers hold theoretical advantages for solving certain types of computationally intensive analytics problems. Combinatorial optimization problems, such as the traveling salesman problem, or complex scheduling tasks, could potentially see exponential speed-ups with quantum algorithms. Significant research is underway to develop practical quantum algorithms and hardware. The long-term integration of quantum capabilities could transform how we approach and solve the most intractable optimization challenges faced by science and industry. Case study: analytics software. Shaping intelligent urban futures, autonomous systems and smart cities are prime domains for advanced analytics software. These environments involve managing vast networks of interconnected services and resources. Effective urban planning demands sophisticated tools for optimization and decision support. Analytics software enhanced by AI and cloud computing is indispensable. It helps design, implement and manage future urban ecosystems. The goal is to create efficient, sustainable and resilient cities. Navigating the path forward. The enduring evolution of analytics software. The transformation in analytics software has been significant. From manual methods to powerful tools, it underpins decision-making across industries. Future advancements depend on collaboration and interdisciplinary approaches. Combining analytics with AI and data science will create impactful solutions.